Okay, and so our next guest is Ron Kita. Now, Ron really needs no introduction. He has attended every single APEC conference to date, and he's finally agreed to present on his approach to modifying gravity using electrets based on his patent for gravitational attenuating material that uses an organic-based material where the electrons of the dielectric are reconfigured through the use of electrostatic, magnetic fields, or photonic or actinic radiation to render the dielectric less interactive with gravitational forces. So Ron, I can see that you're here.
I'm on board here.
Wonderful. Yes. My apologies. It's a little bit of a bumpy ride, but
no, I've known Ben Solomon for years, and a great guy. There's a lot of things I have to get back to him on because I can't really get into it now. But what I must do, without reservation, I must have a warning, because in reviewing the material that are in various publications, there are a lot of disclaimers and warnings on making electrets. Electrets involve high voltages, they involve molten materials, and they involve dielectrics of various toxicities. My electrets are not, they're high voltage, obviously. They involve molten material. And also, I saw a comment, Ron Kita uses mothballs in his electrets, but these are not really, I mean, 1,4-paradichlorobenzene is the common mothball you can buy. I actually buy some at my local grocery store. But what I'm using is something called 1,2,3-trichlorobenzene. It's only one atom extra of chlorine, but the configuration is different. With paradichlorobenzenes in the para position 1,4, you have opposing chlorine atoms, and it's nonpolar. With my 1,2,3-trichlorobenzenes, I have all the chlorines located at the top with 3 hydrogens at the bottom. It's very polar. And so anybody who thinks it's normal mothballs, I must warn them, do not consider it. There's an additional hazard to using 1,2,3-trichlorobenzene. And so anybody who wishes to proceed beyond my warnings, do so at their own risk. So it's something that I read MSDS sheets. My mentor, Dr. William Rhodes, would always send me an MSDS sheets on certain chlorinated materials. He said, Ron, he said, the target organs are your liver, first of all. And he said, you can get aplastic anemia or leukemia. And so the warning is, these are things that, oh, before I forget, that's the end of my warning thing. That people who want to proceed at their own risk, not on my account. I was always wondered why benzene was so toxic, because everything I deal with is benzene related, even though it's chlorinated or so forth. And what I found out, benzene is a simple hydrocarbon, 6 carbons, 6 hydrogens, and it's saturated, not reactive. And I'm saying, why is benzene so carcinogenic? And I looked all over the place, and I finally found you'll see several answers, but being very, very planar, what happens is the benzene cuts your DNA, and that sets up your basis for cancer. So that's where I end the disclaimer. People are on their own, and then I'll start how I got involved in this. You've been on board Gravity for decades, I guess. Yeah. So anyhow, the way I got into gravity shielding was, I always viewed gravity shielding as an information problem. I figured if I could get enough information, I could select the best technique for shielding gravity. And so back in 1980, I go way back, there was something called Dialogue Information Services. Dialogue Information Services was a product of the Lockheed Aerospace Corporation. They assembled a lot of technical data and so forth. One of the things that they assembled, they compiled patents. They had a special patent file. So I took a series of courses up in New York, and my whole goal was to data mine patents, mainly for things that would relate to gravity shielding or anything gravity related or advanced propulsion. And so I got into it, and I took the courses, and I have a brother, Stan Kita, he's a patent attorney. And I said, Stan, I says, you can now search patents without going to Washington and so forth. And I said, you should really use this. It's a new tool. I said, it's $80 a connect hour. That's what we're paying then. We did not have a CRT. We had basically a telex machine. We were acoustic coupled. And I guess we were coupled to place in. So anyhow, my brother said, well, he says, I have law clerks. He says, why do I need this? But then where the utility comes in back in 1980 is in data mining patents. With a patent, you could always look behind in time. And he gave me a call from Washington. He said, Ron, he said, I have a favor to ask for you. He said, I have this patent number. He said, I know what's behind it. It's for my client. My client wants to know what's ahead of it. And I said, well, he said, can you do that? And I said, yes. I said, I'll give you a call. I'll give you an answer in 10 minutes. It shocked him. And so what happened is I became a patent miner. One of my persons that I did pro bono work for was Henry Wallace and his kinematic field patent. Wallace would get calls late at night, and he'd say the military is using your patent. That's all. Just look for the military using your patent. And so I was at Villanova. Wallace worked at GE Valley Forge Space Program. And if you're not familiar with the patents of Wallace, there are 3626, 605, 3626, 606, and their kinematic field. He doesn't use the word gravity. He produces a signal. The best thing he can do is, I use Rex Research. I don't know how many people are aware. I'm Robert Nelson's the guy behind it. Very interesting guy. It's been there for decades. But anyhow, there is a whole thing on Rex Research and the work of Wallace. So anyhow, I managed to reverse patent cite Wallace, and I finally found a connection to China Lake. And a person by the name of Stebbins, which I found I got the name wrong, he was doing a pulse repetition amplifier. And so there was this China Lake Wallace connection that it also appeared in the New Scientist. It was Valentine's Day, 1980, the 10th anniversary of the issue of the Wallace patent. And it says how the military, even the New Scientist knew the military at China Lake was working on it. And also, in terms of all this technology, SAIC is probably familiar with Paul Murad. He knows that it's a private corporation. At one time, Admiral Inman of the Navy was behind it. The electric propulsion study, which Dr. Frank Mead of Enigmatic Sciences Edwards, he gave me a copy. It is really a sort of an introduction into electrogravitics, Brown and everything. And there's only a few copies out there, but so anyways, this became very useful. And the way I met my mentor, Dr. William Rhodes, I met him on Usenet, and before there was the World Wide Web, I was online. After I got beyond my work on dialogue searches, I found that I could get a lot of information off Usenet, and Usenet is still in existence. It is now classified as Google Groups, and the post from 1997 where I met Rhodes is still on there. It's I see Rob, my good friend Rob Chambers is on there. Uncle Slacky from the British Aerospace Green Blue. Yeah, great, Bob. Anyhow, I'm trying not to read and get distracted. Anyhow, so I met Dr. Rhodes on Usenet, and oh, I'm sorry, I have to give Bob a plug. I think Bob has on, I'm not Usenet, I think Project Green Glow is now back in operation again. And through Uncle Slacky, Rob Chambers, there's good stuff here. But so I met Rhodes on the Usenet. Usenet comprised, I think, 2,300 various topics. It ranged from photography to artwork to car repair. It had sci physics, sci materials, sci chem, all this. And there were certain ones that I monitored, and there were certain ones that Dr. Rhodes monitored. And if you go to Google Groups, it's part of Google now. They picked up the whole entire archive as far back as 1982. And I find it on occasion. It's called Gravity Shield Offer by Dr. William A. Rhodes. It's an honorary degree. And in there, he describes, he says, I am 81 years old. I am poor health. I later learned that he was suffering from Parkinson's, and he made an observation. I don't know the exact date of when he observed this. And he says, I am of 81 years old. I'm in poor health. And he says, I discovered a 14% gravity shielding in a material. And he says, I do not want to make this material public domain. He says, if you send me $2, I will give you a description of what I saw and how you can go about researching it and then subsequently patenting it. And so there were only, oh heavens, I think maybe 5 of us replying, Jim Cox, and some of them are now gone. I think Jim Cox from, Jim Cox and I had Anti-Gravity News, which is Dr. Patrick Bailey he was of Lockheed Missiles. He still hosts the website. The website for Anti-Gravity News is Padrak, padrak.com/AGN, and that'll cover a lot of things on electrogravitics. It'll give you a lot of biographic references. So anyhow, with Rhodes, he was criticized heavily on Usenet. The people on Usenet, they said, why don't you give it public domain? And then someone said, well, since it's only like 6 pages, if it cost you a nickel a piece and 30 cents postage, you were making a profit on it. And so he got hounded on Usenet. And so he was happy. Yeah. So anyways, so the whole thing was this transducer that Rhodes observed. He got the transducer from a friend of his, and his discovery was purely accidental. And when he was moving the laboratory over to his laboratory, he had a beam balance scale. And what happens is, I'll use this as an example. When he put the transducer on one side of the scale at a certain weight, when he moved this transducer to the other side of the scale, it was off by 14%. The reason why Rhodes, he picked the transducer because of its heavy weight. The transducer weighed approximately 500 grams. We looked for something. His assumption was there was going to be something wrong with the scale. And we saw this, he didn't envision a scale being off by that degree. And so he later realized that on this transducer was a thick metal plate. And when the metal plate was on the bottom, it had one weight. And then when he brought it across to the other pan, then he balanced it out with equivalent weights. When he did that, he realized what happens is the dielectric material on the bottom of the transducer, that was shielding the plate on top. When he flipped it over, gravity was working directly on the plate. And so he became highly intrigued by this, and then he started testing it. And he put it through he even did an off-center flow test where he put it on a piece of styrofoam and put the weight off, and he filled his bathtub with water. He says if gravity is going to affect this being off-center, it's going to pull it across the bathtub. And he says you could see it go across the bathtub. And if you put your finger the transducer would hit your finger. You could feel a slight force against it. And so with Rhodes, he looked at it, and he had what he called panoramic laboratories. It was a building behind his house. Rhodes lived in Phoenix, Arizona, and he worked a lot of times in San Diego, and so he would leave the air conditioner off and go to San Diego. Well, what happened is he ran all his tests on this 14% weight loss, and I should add, the dielectric material in the transducer was 1/4 of an inch thick. And so when you take if it scales with thickness, approximately 2 inches should give you 100% gravity neutralization. And so anyways, well, he said the sad part was when he left to work in San Diego, he came back a week later with the air conditioner off. And what happened is, before he left, he wanted to see what the material looked like. And he knew if he opened the case, he was very worried, because he assumed that the material inside of this case was, he knew it was a piezoelectric transducer, because he tested it, and it pumped voltage in, and you got ultrasonics out of it. And the guy who he inherited the laboratory, he worked on ultrasound equipment for hospitals. So he had a lot of piezoelectric materials, but this was the heaviest one. And that's the one he chose to stress the fulcrum of the scale to see if it would go given proper balances. As Rhodes said, he says, this gravitational material, he says, I didn't find it, it found me. I'm going to go off a second. I want to, in terms of who Rhodes was, on Usenet, they hounded him. He got much disrespect, but his degree was honorary. He worked for the War Department, and I think during World War II, he wasn't in the service, but he told me, he says, I work on submarine detection devices, and one of the projects was called Aeroid, A-E-R-O-I-D. He says it will probably stay classified for a very long time. But Rhodes is also, in terms of the substance of who he was, he invented the first photo amplifier, photoelectric tube. He was a man of the tube age. He invented it with Lee DeForest. A lot of people may not know who Lee DeForest is. Lee DeForest was the father of the radio, because Lee DeForest invented the Audion, which is the amplifying, the triode. He invented that. And so if you look at patent US 259470, you'll see Rhodes' name and Lee DeForest on the same front page. So Rhodes, in terms of having my respect, because in terms of, I look at Rhodes, I saw what he saw, and I wanted to make sure this guy, in terms of having credibility, also, I'm not sure it's handy here. Rhodes is the inventor of about 20 patents, some of them on solar energy. He used bromine circulation fluids. So anyways, where do I want to go? So with my Electrets, since people are wanting to know, an introduction to Electrets, there's what is called the, I'll use it simply, this is Tom Ballone's, everybody probably has it, is electrogravitic systems 1 and 2. The simplest electret is called a homocharge electret. If you take a piece of plexiglass, let's say this is plexiglass, and you put a positive charge on the top, I'll just use a positive charge. What happens is this is positive, and then by nature, the surface will be negative. So it's called a heterocharged electret. What I'm involved with is not heterocharged electrets. It's called a homocharged electret. A homocharged electret, I tell people, a homocharged electret is usually a binary set of materials. One is electronegative, or I use the word dipolar to be more accurate. It's dipolar, and your matrix is nonpolar. And so when you make a heterocharged electret, it's in the patent US 1890943, is a discussion on the conversion. All electrets will start out as heterocharged electrets, which means you put the electrode on the top, the surface will be the opposite. When you're making a homocharge electret, what happens is you will, it starts out hetero, this, whatever this will be, this will oppose, then you charge it, and then with the electrets, by nature, to follow the rules of making electrets, you must foil wrap them. What happens is you must short circuit them out to retain the dipolar, or it's much like in the days of when people made soft magnets out of iron. A horseshoe magnet would always have a keeper on the bottom to entrain the flux within the horseshoe magnet because the material was soft. Also, when you make an electret, you want to allow the charges to redistribute. I mentioned in the US the patent that when you start out, you have a heterocharged electret. And what happens is, if you monitor the charge on the electret, it's foil wrapped. It's the way I monitor I know what the electret is doing. I weigh it, and weighing it gives you an idea of what's going on, the relationship with charge to weight. What happens is a lot of these, like I said, these things are diode-like. It depends on the materials. A lot of times the electret will drop down and then it'll come back up again. And what happens is it's all related to discharging and charging. And like I said, also depending on, there's something called charge additives. You have a dipolar material, like I use 1,2,3-trichlorobenzene, and then you can use naphthalene or any para material that's nonpolar. You matrix them together, and what happens is you'll have a change in weight that reflects what the charge is doing. And there's a YouTube. It's the STAFE 2016. It's the presentation is by Dr. Martin Tamar, and it goes back, like I said, it's 2016. He has a presentation on my electret, but in there he'll have the weight loss and the weight gain, and he attributes the weight loss to outgassing. But what happens is nobody in the audience or the members are there, they never see the upside is not talked about, because a homocharge electret will change its weight, and in most cases it'll come back to normal. This is almost similar to what Ben Solomon was saying, this like hysteresis. And also, I want to say, it varies upon material. And I said, Tamar, after I saw a Breakthrough Propulsion Workshop 2016 Estes Park, it is available on YouTube by searching Tamar Electrets. And also, he has a paper. It's called propellantless propulsion, and what it is, it has electrets. If you, I do a lot of control F to see the number of citations that electrets have in a paper. In Tamar's paper, he has a citation. There's the word electret is mentioned 52 times, and I best go to my notebook, because Tamar also has a patent based on this propellantless propulsion patent, and it's really most unusually titled, and I want to get it correctly. So in my notes, I wrote it down, and I now have more notes than I can reasonably. One second, I'll find it. But the thing is, okay. Okay, here we go. I wrote this down. It has the Tamar. Please. Okay, okay, anyhow. The Tamar is spelled Tajmar. So if you try, I was pronouncing it Tajmar, but it's Tamar, Taymar. And Martin, he's at the University of Dresden. And the AIA paper, let's see here. The AIA paper, okay, is
Oh, and Ron, sorry, it's Tim. In chat, people are asking for links to this as well. Is that something that you could send to me and I could add
I'll
this?
tell you I'll tell you what I am going to do. I will. There's an. No, it's. I have so many notes, but yeah, I will. What I will do in an email, I will send websites, and I will for a second. Since you mentioned that, what I am going to do, I'm going to step out of here for a second, and I went through my my files. And is everybody familiar with the Electric Spacecraft Journal? Is that a familiar publication? I don't know if it's familiar or not, but Electric Spacecraft Journal is by Charles Yost. And Charles Yost, in terms of, it's not known to many, but Charles Yost, according to some sources, they claim that he was running an alpha experiment, but his main research is on electrogravitics. I met Charles Yost. There's for those who are interested in the various lectures on the Temple University Frontier Sciences that I was a member of. They hosted a symposium on Thomas Townsend Brown, and if I will send it to you, but Nancy Klenda was the person behind it, and there's a video that gets in to the work of Thomas Townsend Brown. It ran for I think 2 days, and I will send stuff. And also, what I can do is I looked at the Electric Spacecraft Journal, which is, in terms of being timely, Charles Yost has no copyright. He says as long as you cite the origin of this book, you can publish it. And so what I'm going to do, I'll scan some of those and I'll mail you the scans to the Electric Spacecraft Journal. And also Jim Cox, this is in sort of bad shape. He put something out called Anti-Gravity News. And in terms of anti-gravity news, it's the same thing. It's very much like the Electric Spacecraft Journal. And so in terms of pulling things out that are not copyrighted and can be shared and sent, and also while we're on this topic or off of this topic of Electrets, the infinite energy is mostly devoted to LANR, cold fusion. I was a friend of the late Dr. Gene Malov, and they do give a reasonable coverage of breakthroughs in propulsion. And so, what else? I'm trying to think of where else I am. I'll try to get, let's see. So getting back to Electrets and the dipole moments, when I look at Thomas Townsend Brown, what intrigued me most was his boat. He had a boat, 11-foot long boat, and the 11-foot long boat was a combination of litharge and so forth, and it was radio controlled. And it I don't know if there's any videos, but supposedly it propelled itself along the lake. And Tom Valone of the electrogravitic book, he said the whole key to Thomas Townsend Brown was the pulse capacitors. And I believe that. And for the longest time, I never bothered. I never got involved with Thomas Townsend Brown. I merely accumulated his information. I actually never really doubted it. Thomas Townsend Brown came out of Philadelphia, and he had a company called Electrokinetics out of Ballackinwood. and he later moved to Catalina Island. He got involved in petrovoltaics, and these were sort of like rocky. They weren't electrets. They were sort of like rocky electrets, and so in terms of parallels, and then, like I said, with Rhodes, when I first got Rhodes's papers, there was 5 pages there, and I was intrigued by the 14% loss in a 1/4 inch thick material. And Rhodes was from the days of the electron tube. And myself, back in '62, I bought an Electret microphone. And because a lot of your other carbon-based microphones had you had to supply them with electric power to get them to work. And so I became intrigued with Electrets. And I thought that an electret is from the word electrostatic magnet. When you conjoin the words, you get electret. And so I always wondered, what different properties would electret have over a magnet? And in terms of making them, I was never, in terms of having a high voltage source, and the classic Electret. This is my first Electret, and I don't know if you can see it or not. What I use an aluminum backplate, and it's balsa wood to give it the depth. And this is the classic Electret. Iguchi invented the Electret. He used a mixture of 50% rosin, but rosin is really a generic name. What rosin really is abiatic acid. Abiatic acid is a phenanthrene ring. There is a benzene ring relationship between, if you look at abiatic acid, you'll see. And then he compounded it with carnauba wax. And so with the Electret, what you want to do, I'll make a step aside for a second. In terms of when we look at gravity and we look at electrostatics, the people, I could never get Benjamin Franklin. I always wondered would Benjamin Franklin have linked static electricity to gravity, but I never found it. But the old scientists, they said gravity is probably a phenomena that's related to electrostatics and heat, or the mass of the object, in a strange way. So anyways, my view is when we in our everyday world, when we experience electrostatic shock, when we walk across the rug, we give a shock. That shock is on the surface of the material. It doesn't go into the heart of the material. When you make an Electret, it's the only material that I know that when you make it, you want a little bit of current, because my Electrets, everything I have is, I don't really go above a dielectric constant of 10. And I use a milliamp meter and to make sure that I see a slight leakage. It's almost as though you're taking a capacitor and you're wanting it to leak or break down. And so what you do is you hit a certain balance, because with an Electret, you can rupture them. I have made Electrets where I've hit them with 20,000 volts, and you're better off taking a low voltage, polarizing it, and then as it solidifies, you can bring the voltage up. If you hit it all at once, because in one of the disclaimers, in terms of the unforeseen things that can happen when you make an Electret, these Electrets have an electro-rheological response. And I use a aluminum screen on a majority of my Electrets, mainly because what happens is I can add the dielectric. When I start out, this screen will be filled to the top with the dielectric. When I apply high voltage to it, what happens is the rheological response, when you start out with disorder and then you order it, what happens is you have a change in density, and this will contract. And so then I can add enough dielectric to fill the cavity. Otherwise, a large section of the cavity will not make contact with the surface. And so in terms of using, you can use a solid plate top and bottom, but in terms of seeing what's going on, this one that was made, Professor John Vasilio at Villanova, we had a lot of discussions on material science. He was of Greek origin, and I learned a lot about eutectics. Eutectics play a role in this. Eutectic is the Greek word for easy melt, because some of these materials, when you put them together, they will, even though they're solid, and they will have a melting temperature that's below room temperature, and you cannot use them. And so with this material, I was talking to Vasilio, and the Electret has a lot of internal stresses to it. When you polarize the material, because when Dr. Rhodes, when he opened the casing, because Dr. Rhodes thought the material inside the cavity was a piezoelectric crystal, but it was a large source, and he couldn't envision how you could get a transducer larger than this out of one crystal. And I told him, I says, well, it's not a piezoelectric. I said, it's an Electret. And I said, that's why you can get to that size, because you can polarize it. And when you upset the polarization, that's when you create your piezoelectric response. And so with Vasilio, I brought this one to him, and I said, the way it fractures, I said, this thing fractures very usual. And he says, that's due to the, he used the term frustrated material. These Electrets, in terms of having a lot of stresses within them, because I told people years ago, I would like to design a material that has all the structures so orientated that gravity could not induce an effect upon it. Because when we look at a bridge, for example, you look at the concrete, there are gravitational stresses set up in there. And I said, well, is it possible that you could make a material so rigid that gravity could not act on it? And so we looked at the stresses and so forth. And in terms of testing materials, we would test the material on an oscilloscope in terms of getting a response off of it. And some of the Electrets that I made were, he says, you got some great Electrets here, but some of the Electrets that I made, even though they were great transducers, they did not modify gravity. This one here, being the first one, do I have it? Anyways, when I first made it, okay, I had a small digital scale, and I put it on the digital scale, and if I set it on the digital scale with ease, without tapping it, or just set it on smoothly without accelerating the scale pen, it would come up with 0, 0, 0. And even though this has a weight of 150 grams, I knew there was something wrong. It was not doing anything to gravity. And so at that time, I was in communication with Colonel Rex Schleicher. He invented the NEMPS, which is, the title is Nonlinear Electromagnetic Propulsion System. And I said, Rex, I have the problem with this. I said, my brother's a patent attorney, and he's skeptical of what I do. And he looked at this, he says, Ron, this cannot be. He said, you have a material you cannot weigh, but yet it has this weight. And so when I talked to Rex, I explained to him, I said, I have a material. I said, I know it's not modifying gravity. And I said, I have this inexpensive scale. And he says, well, your scales work, these inexpensive scales, they work on F equals MA. if you know the acceleration and the force, or the accelerate, you determine the weight through an acceleration on this. So what happens is he says some scales work that way, because I have a different scale that will weigh this correctly, and the cheap, inexpensive scale will not give me the weight. And so anyways, I talked to Rex, and then I realized, is it possible? I've never, it's a place that I'm not really interested in going, but in terms of inertia reduction, that zero weight, when I just slid the electret onto the scale, did the zero weight mean inertia is reduced, and that's why it gave me a zero reading? In terms of having time to go back and look at possible inertial neutralization, because the equivalent principle, gravitational effects are the same as inertial effects. And I don't know whether that is true or not. So anyways, the Electret materials, as I said, what you are building when you're building an Electret is you are largely building a diode. In terms of getting high performance out of these binary materials, one is polar, one is non-polar. To bring up the electrostatic effect inside the material, there is something called a charge additive, and charge additives are very strange, almost semiconductor. If you look at non-metals, they're included in there. In terms of my library on Electrets, a good source for Electrets, oddly enough, are the Xerox Corporation. The Xerox Corporation, in terms of their toners, a toner is basically like an Electret material. It's electrostatic material that is electrostatic for a brief period of time. And another source of Electret patents is the 3M Corporation. When my patent was in an application, I contacted the 3M Corporation, and I met Dr. George W. Buckley. He was the CEO of 3M Corporation, and he became interested in what I was doing. And we had exchanges back and forth. And what happened is, he says, Ronnie, I have a few projects. He says, I like what you're doing. We'll stay in touch. And he turned me over to a woman. I didn't know her title. She turned out to be a PhD in product development. And I would send her stuff to hold for Dr. Buckley. Dr. Buckley was an electrical engineer. And so in terms of sending her material, one of the papers that I sent her was a paper by A.F. Rullan, R-U-L-L-A-N. The paper is entitled UFOs and Odors. It's the odors that UFOs emit. And so when she saw that, she says, we cannot have the 3M Corporation tied to anything that is UFO related. And we broke off contact. And Buckley left 3M about a year after that. And so, but in terms of dielectrics, the UFO and odors, see in Rhodes's paper, the only thing he has there to go by is the odor. He says, Rodney, I opened the cavity. The cavity had the strong odor of paradichlorobenzene. And Rhodes says, I know there being non-polar, that there is no piezoelectric quality to paradichlorobenzene, but yet it has this odor. And so I told Rhodes, I said, I know what you're saying. And I said, I studied this paper by Rullan, and one of the odors that UFOs give off, it's a mothball odor. And so I said, I don't know whether this could be viewed as any truth or not. And so I said, I studied olfaction, and olfaction, our cutoff on smell is a molecular weight of about 300. Also the shape of the molecule. It's a strange phenomenon. And so I said, in terms of finding the material that was in your transducer, I said, it probably has a molecular weight of less than 300. And we know that he lost the electret when he left his building air conditioned for about a week. And he says the limit of the temperature inside his outdoor laboratory, he says about 140. And so that's when I went into a lot of the, I cannot, I will have a book on my, a second, hold on. Yeah. I don't know if you're doing anything in material science. This is the Alpha Azar catalog. They've now changed hands. They were acquired by Fisher Scientific, which is now Thermo Fisher. And so I went through, I cannot tell you how many pages there are on aromatic materials. And so after going through them, I started to look at the weight being under 300. It had to have a good dipole moment. And so that's why when I, it's in the patent, it's the trike, you know, you can see this one, maybe it works better this way. Anyways, you have 3 in trichlorobenzene. This is 1, 2, 3 trichlorobenzene. What happens is the sheer effect, when you have a molecule and it's polar, it's obviously polar by the distribution of the electronegative chlorine atoms. And when it crystallizes, it can, in many cases, it crystallizes back in a polar form. And so I identified trichloro, 1, 2, 3 trichlorobenzene, and I couldn't, I tried working with it as a pure material. And what I never realized with 3 trichlorobenzene, it's very, very polar. So you have three chlorines here and 3 hydrogens here. When you put another one on top of it, the chlorine will flip over to the hydrogen. And as a crystal unit, it will form a non-polar material. And because I could not understand why things were not working out well, is because on crystallization, you have a material that wants to be non-polar just due to the distribution of the electronegative charges, electropositive charges. And I think the unit cell with the whole crystal, it's a 2 this way, and then it's 2 this way, making it very, very non-polar. In the patent, to get an effect, I use a matrixing material. I like carnauba wax because it makes a very, very good neutral matrix, not really any crystallinity to it. And so what I did is I spaced out to keep the trichlorobenzenes getting together and neutralizing. I effectively spaced them out with carnauba wax. That way you can get them to work. I later found out that the materials that I use, at one time we had our dielectrics were chloronaphthalenes. There's a whole slew of chloronaphthalenes. Once again, some of them are eutectic. You take solids, you mix them together, and you'll get a liquid out of them. A lot of them were used in transformers and so forth, and they were actually abused. They were prolific, and once again, they can cause liver damage. So I think around 1971, you were forbidden to make certain chloronaphthalenes for industrial use. And the material, oddly enough, that Rhodes had, the transducer, on the transducer was the term kilocycle. And I think it had something to do with the anniversary of Hertz. They changed the term kilocycle to kilohertz in honor of Hertz. And so we knew that the transducer we were looking for predated 1976. It was probably military because in terms of, Rhodes kept thinking it was a medical transducer, but with a medical transducer, if you have something that melts at like 140, it's not really a commercial product. And I talked to Rose. I said, Rose, I said, based upon what you have here, I said, this material, I said, was at probably one time, I'm not sure whether it was production or experimental. I said that basically they only have the cyclage on there, and I says it has to be used at a temperature that is probably in the ocean. I said it's probably used by a submarine, a destroyer, or so forth. And so Rhodes really tended to agree with me. He says that he says in terms of when he broke the material, he says it fractured quite readily. And by fracturing quite readily, he says it could never have been a piezoelectric driver to drive an ultrasonic tank or to ultrasonically stimulate something. He says it was basically a listening device. So it puts it in the realm of what's his name of hydrophones and that technology. And also, since going deeper into trichlorobenzene, there's a series of isomers. You'll have you'll have the same composition, but the position on the benzene ring will vary. And the materials that I use was say by no longer being made, it means you have to make them. And some of these old dielectrics, they were made by Union Carbide, Hooker Chemical, Buffalo. I use the word Love Canal, New York, and they were made at elevated temperatures. They were made at elevated pressures, and so in terms of where I am, I always every day, constantly, I read my patent, I run experiments, and I try to look at alternatives. And in terms of the best material that I can see so far is still the 1,2,3 trichlorobenzene and another substitution, because you can add something to the ring and remove a hydrogen atom. And these materials are not made. They're not. I avoid going to China because I do not wish their involvement with anything that I might get from there. But what it comes down to is I must fabricate a special 1,2,3 trichlorobenzene. When I realized my materials were no longer made, and I had to make them myself. With chlorine, chlorine is a valence of -1, oxygen is -2. Chlorine is extremely reactive. And I thought, well, you're basically going to take benzene and chlorinate it to double the atomic weight of benzene to get the three chloros on there. And so by weighing it, you can see the degree of chlorination. What I never realized that to avoid a lot of isomers, which are unwanted, the isomers of 1,2,3 trichlorobenzene are nonpolar. And so you want to avoid them. And I realized that in order to get this to happen, you have to catalyze a chlorine reaction. And I go, not only is chlorinating benzene risky, you have to add a catalyst to it to speed up the reaction. And so luckily, courtesy of Tanya Slowacki, she appears on here once in a while. Tanya Slowacki is material science, Penn State University. She's well connected, a very good friend of mine. She would come down and film me. Her parents live in nearby me, and she would stop by and videotape what I was doing and has some of my early research on there. And so she put me in touch with a woman who holds several patents on catalysis. And so in terms of doing it simple, I have to go and I have to generate. I don't want unwanted isomers, because with isomer separation, especially with these materials, a lot of times you can separate isomers, you can freeze them out, you can boil them off. But with these isomers, they are so close that it's very, very difficult to do. So it's best to fabricate them shearly by using a catalyst. And so that's where I am. What I've managed last year to make what I'm driven by. I look for a high index of refraction seems to be favorable to this, because even Rhodes looked at the material, and it was. He says it's very refractive, and also I tell people, since when you make an electret, as I said, you want the electrons to go into the material, because everything we experience in our everyday life, when you throw a spark, it goes onto the surface, and with the electret, you want trapped electrons, and you want the trapped electrons to polarize the benzene rings. In terms of benzene rings, okay, I'll get the benzene rings. In terms of superconductors, we have Johnsville Naval Air Station nearby us, and I had a friend of mine at Michigan State University. He knew I was into superconductors, and I was into superconductors mainly due to the Podkletnov experiment. Because I thought gravity was solved. When I saw Podkletnov, I thought that where's he at? I thought Podkletnov would be the end of gravitational research. I thought it would be mastered. But my view is, and also the work of Johnsville, that they were trying to make superconductor materials out of benzene rings, because a benzene ring in itself is basically a non-bulk. It's a electron ring material that is not interconnected. Johnsville Naval Air Station was trying to find a way of linking up these ring currents and producing a superconductor. And myself, I said, well, maybe to shield gravity. Very good, Rob. Yeah, I'll get into graphene in a second. People view benzene as low technology, and I look at it as a superconductor material. And also, when I saw graphene, I go, because when I wrote my patent, I was aware of graphene. I had no access to graphene. I'm not sure how large of a sheet you can even get nowadays, or how much production value it is. But since I had no experience, I didn't have any reason to run an experiment with it. I then realized graphene is a conductor. When you are shielding gravity, what you basically want is a dielectric. And it is possible that the graphene, especially with these they have a twist angle that they put with graphene. The twist angle, when illuminated, gives a moire appearance, this iridescent or pattern. And whether the graphene will ever get there, but it's just in terms of being a conductor, I ruled it out. I thought, well, I can simply add the word graphene to the patent, but I really didn't have a basis. And I said, well, it's a conductor. However, where graphene is becoming useful nowadays is in electrodes. Graphene electrodes in batteries, as Mark will probably know, I think the latest developments. I'm not sure if they're commercial or not, but in terms of getting to an ultimate battery, it'll have graphene electrodes. And when you're making an electret, you also have to be considered your electrodes. My electrodes, most of them, I do use. Well, obviously, what is very accessible as an electrode material is fly screen, aluminum, and a bottom plate of aluminum. Also, there are people, when you make an electret, you are also affected by your electrode material. There was a guy in Brazil, Mascarenhas, Mascarhanas. He did a lot of work with Electrets. He was a grad student at the Sao Paulo University or the equivalent, and he was a grad student, and he'd work late at night, and he'd prepare Electrets, and he used carnauba wax, since it is a product of Brazil, and he would pour it into a cavity that was iron, and what he'd pour it in, and then he'd turn it on and let it polarize overnight, even though it's not necessarily polarized. And in the rush one evening, he prepared the Electrode material. He poured the carnauba wax into the mold, and he left. And then when he got home, he realized he forgot to turn on the high voltage. And he came back the next day. He opened the cavity, and there was an Electrode. And there is something called, well, this goes back to the days of the electrophores. There is something called contact electrification. If you put certain materials on a surface, they will they will polarize due to the tribo, T-R-I-B-O electric effect. There's a series. It's called the tribo-electric series. It's a vertical chart. On one side, the very bottom, the extreme bottom, you have the electronegativity of Teflon due to the fluorine. And on the top, you have a hydrocarbon. It's usually silk or something like that. And you have the extremes. If you look at the type, if you take any of the, in the middle of the triboelectric chart are metals. Metals do not charge. So if you take any of the two dielectric materials of opposite polarity and put them together, you will generate electric charge. And like I said, this guy who put it into the cavity, due to the contact, you will get contact electrification, which surprised me. It's called the Costo, see, Costo Ribeiro, R-I-B-I-E-R-O effect. And so these things can be charged by surface contact. And so with graphene, like I said, graphene, will it play a part in shielding gravity? In a strange way, they're pushing the limits of getting it very, very superconductor-like. And it may, from that, I do not dismiss it, because I've seen different people claim that you can get there via graphene, but like I said, in terms of, I've never tried to access large sheets of it. And where else? I'll go to my notes in a second, but how am I running? Have I run through? Have I run over time, or where am I?
Well, actually, you have just a little bit, Ron. But do you need more time to kind of keep going on this?
Well, I'll tell you what. You see, in terms of question and answers, in terms of liability, a video is good in many regards in terms of transferring information. In terms of questioning answers that may be proprietary, or if people want to make comments about my lecture, I'd like that. I have no problems. But in terms of liability or anything, they can email me a question and I'll respond to them with no problem. But questions and answers it can be kind of legally lethal. It's just you don't know where it's going to go. But anyhow, this I didn't realize I was up over an hour. Also, I'm going to say, I'm going to take a look at my notes. And oh yeah, I will do running over. I will talk about the various, what I call the Woodstocks.
Okay. Well, if I could jump in very quickly for a second.
Okay.
And so, actually, Jeremiah had a question, but what I was going to say is,
Yeah,
if you don't want to do that long of a Q&A session, if you'd
yeah.
like to talk about some other things, you mentioned talking about the various wood stocks, but we could do that. Do you want to go for a
Yeah,
bit more?
because like I said, it's just in terms
Okay.
of
Okay.
it's just some things it's not wise legally to answer. It's just I go why? So if I
Oh yeah, yeah. Well, and I wouldn't want to push you for anything like that. I think it's always fair to say I don't feel comfortable talking about this, and then we can always do the disclaimer, don't try this at home, especially
yeah
with what you're talking about, right? A lot of these chiral structures,
yeah
these are dangerous
oh,
chemicals, so we don't
yeah,
want
well,
people
I
playing with
mean, yeah,
dangerous chemicals.
I mean, people don't view a paradichlorobenzene. It kills moths in certain concentrations, and it is toxic. I mean, we stuff we buy, sulfuric acid. It's just things you can buy in a
Yeah, yeah.
so that's why I stay away. I'll tell you what, if well, anyhow, what I will do, I'm trying to think of what I can do in terms of that's how I got into Electrets. Rhodes was an honorary PhD, very accomplished, a lot of patents. Every day I go back, I look at his notes, and he was, in terms of being any mistake that he made was accidental. He did a lot of discouraging me from going into certain materials. He said, Ron, he says, you're going to get leukemia, which is risk of leukemia, or something is. One thing I'll mention, because I always am concerned about toxic materials. What I did find is that paradichlorobenzene that people use. In fact, some people's houses, you can go into their house and you can smell the paradichlorobenzene. And I read every day, every week I go through all the journals and so forth. And one thing I didn't realize about the paradichlorobenzene mothballs is somebody found out that there was an incidence of hearing loss with the use of paradichlorobenzene. And I have one relative that both of them had a great hearing loss, and they had an excess use of paradichlorobenzene. I'm not saying it's cause and effect, but I'm saying it's something that you never think of the toxicology of it. And I never told Rhodes that at one time I worked in the foam industry, and I worked with toluene diisocyanate, which is an insanely, some of these materials. One of the women that worked in the lab with me, Joanne, in terms of what toxic is, she says, Ron, I was working late last night. She says, I went outside, she says, and I looked at the lights and it looked like it was going to snow. There were all these big shimmering circles around the lights. I said, Joanne, I said, that's the first sign of cyanide poisoning with isocyanates. Some of these things are so toxic. So anyhow, that's it. It's the toxic materials. I have something additional. One material that I have it right here. I wanted to have things close to me. Mainly, I can just keep on going. In the construction of Electret, okay, I'll go into the construction here. This is a 4-inch PVC pipe cap, and they run about $3 or $4. And when you deal with, one of the reasons why I'm very cautious with molten hydrocarbons, aromatics, is the way this is constructed. I have a small pinhole at the bottom of that goes through the PVC, and in the bottom I have a completely round disc of aluminum that's tight to it, and I run a lead into it, and then there's another plate here. So you basically have two plates with a PVC layer in it and a tiny hole, maybe 32nd of an inch, if that is, just enough to get a wire through to take the high voltage from the outside plate to the inside plate. And I made one last week. And with molten hydrocarbons, they will dissolve epoxy quickly. I tried certain gasketing materials that are silicone. used for head gaskets. They attack chlorinated materials at high temperatures before you even energize them. Will eat up a lot of things. And I've had leaks that I had never expected. I mean, and one leak we had last week, it was simply, I found out the best material to seal the electrode to the bottom with was a rubber material. Because with rubbers, you have long, stringy molecules. The reason why they use thiacol. Thiacol is basically a matchstick rubber with sulfur and ammonium perchlorate, and so the average glue will not hold. And I made the mistake of not letting the rubber contact cement go overnight, and I let it go 3 or 4 hours, and I poured it in. Even though there is a lot of mechanical sealing to it, within a minute, it was leaking the molten material. And so in terms of even soldering does help. If you do solder the wire in there, it prevents leakage. But in terms of things happening unexpectedly, also when you're dealing with chlorinated, the highest I go is trichlorobenzene. When these things are molten, if you get a spark, you will set the electrode on fire. It's just there's that much hydrogen. These things are in the solid, they don't want to combust, but when you get them hot and get a spark, you will get a fire that puts out some rather nasty materials. So in terms of the way this is constructed, a plate here, there's a plate that fits very, very tightly on the inside with a small connecting wire, and that gives you the bottom electrode. The top electrode, as I mentioned, I like having a material that I can see through because these things have electrorheological response, and a lot of times I have to add to bring this up to full contact. I have to add maybe this cavity comes out to be 100 cc's. I'll have to add maybe 10 cc's due to the electrorheological response to keep in contact with this entire wire. This is a nylon bolt, and this is the lead. This is a paper clip that joins the fly screen to this. And in terms of permeability, I found a good. This is I think it's PET, polyethylene terephthalate. This is a bottom of a polyethylene terephthalate bottle. This came from I think maybe a bottle of Canadian. It's heavy walled, and because the thinner versions I have used in the past are the bottles that use soda in, because what it is, a soda bottle will take a lot of pressure and CO2 doesn't get through it. And what this is effectively a stronger version of that. In the center, there is a nut. This is what the electrode looks like, and there's a nut on there that pulls the thing down the electrode. Also, it is sealed with at least 4 layers of vinyl tape. When I buy my materials, they come in as such, and some of these materials, what they have, all they seal it with, it's volatile. They seal it with a layer of vinyl tape. So I put 4 layers in there because the thing is, in terms of having things not wanting to escape, and also in terms of Electrode Materials, in the patent, I mentioned a material that one of the ones that makes me happy. Oh, this is the one of them. Where is it? Is BZP? Maybe it's not. Oh, this is not. Okay, I don't. It's a similar structure here. It's a. I have a lot of data on here. I have the time, formation, weight, and so forth. And in terms of a more friendly material, and I have to go back to this because this preparation has helped me in some regards, because I went back and I reviewed a lot of things. And I may have mentioned earlier that one of the materials I got involved, there's two materials that are photonics is a big word now. In photonics, you have something called nonlinear NLO, nonlinear optical materials. And I made an electret out of a nonlinear optical material. And then I found out there's something called benzophenone. And benzophenone is one of the more friendly materials. It's used in common sunscreen. What it is, it's a second harmonic generator, which means that you bring in ultraviolet light, you convert it to another frequency. That's how the sunscreen works. We have zinc oxide sunscreen. And I found out that I was going to make a YouTube at one point. I had certain requirements for a YouTube that when I do my weight samples, I always do weight samples of 10, just because it's good practice and you can do certain statistics with it. And so anyways, I was looking at it and I was weighing it, and I wanted to get my scale measured. It's a Sergeant Wells lab scale. It weighs to 100th of a gram, and at one time it was like $1,500. And my friend Bob Sternman gave it to me. A lot of stories with Bob Sternman and gravity. But anyways, it weighs to 100th of a gram, and I wanted to get 10 deviations of weight changes. And the weight changes I wanted were not over time, like roads. With me, the weight over time, that doesn't really mean much to me. But in terms of the inversion, I have certain electrets that I have a heavier plate on, and so I went like roads. I went 500 grams. Let's say I went 500 grams this way, and when I flipped the metal plate on top, I want this thing to weigh, like say, 450 or something like that. That's what I want to see, and so what happened is when I make electret, some of these they will go. I can get to 3 deviations, and sometimes you lose it. I wanted to get to 10, and then I cut it to 5. I wanted to have a flip over, a differential of 5, and benzophenone is there's 2 carbon rings to it, and it's a ketone, has an oxygen. Things ending in O and E are ketones. And what I liked about it is it's a sunscreen material. It's a second harmonic generator, which is really weird. And also, if you look into nonlinear optic materials, it's both. So this is one of the strangest materials, and I saw effects out of it. And I should have built more. Right now, I will go back to the benzophenone. I don't know. It doesn't have the bright refractive properties that I'm looking for. There's a lot to be said there, but right now I'm working on catalyzing trichlorobenzene to a certain material that has this high refractive index. And so, but in terms of nonlinear optic materials, I sent an email out to you. It was one of the, in terms of looking at benzene superconductivity, it's Professor Wehlitz, Wehlitz. He's with the University of Wisconsin. And the best thing you can do is to get an idea what's going on is if you go to Google Images, type in Wehlitz, Wehlitz, benzene superconductors. He has it's an excellent image of pairing up Cooper pairs, and also in the image when this ordinary benzene is stimulated with ultraviolet light, he has it looks like there's 2 electrons or 2 electrons. I forget two paired electrons going in opposite direction, and it looks as though they're entangled. So in terms of benzene and entanglement, I really don't know what to say about it. I wrote Wheelitz about what I was doing with benzene and ring currents, but Wheelitz is in terms. I never got a response from him, but when you see the diagram, in terms of research, there is so much that can be done, in my opinion, with benzene. Also, I don't know if I'll ever see meaningful amounts of graphene sheets. The graphene and the magic twist of the Moiré pattern, they may get gravity shielding. So where I am now, I can leave it off. I am basically making one material. I made tiny quantities of it that had unwanted isomers, and I found that I'm happy with it. The only thing is I have to get up to 100 grams of it, and so that's where I'm working. As I say, any overnight discovery, overnight success takes 5 years. I've changed that a bit, so that's where I am, and if I can go into